There we go. I think I'm recording now. Yes. Yeah, I think it just stops recording whenever my tablet shuts off for some reason. So let me see if I can't find the setting to like keep the brightness up. I don't even know. Display and brightness. Or power. That's what I need. The battery. Nope. And my thing's not working. What is this thing doing? Battery. Take it off low battery mode because it's charging. All right, what did we get for the reaction forces? Did we figure those out yet? You got it?
Negative 5 kips and 5 kips.
Not negative 5 kips and 5 kips. Should be 5 kips each going up.
Oh.
All right. When you do the sum of the moments about A, we get 10 kips times 5 feet, and it's causing a negative rotation about A, so you got to add a negative sign, plus BY times 10 feet, and BY is going to be represented by a positive force going upwards. So when you do the math, you should get that BY is equal to 5 kips going upwards. From there, you do sum of the forces in the Y direction. So that has to equal 0. Let me just emphasize that this is equal to 0. So sum of the forces in the Y direction, you get AY minus 10 kips plus BY, which is just 5 kips. And you get that AY is also equal to 5 kips moving upwards. Pretty straightforward, right? Now comes the shear force diagram. This is what we would use to actually size out the beam to resist shear forces. Now, depending on the length of the beam and the depth of the beam, either shear or bending can govern, but we're going to go over bending next class because to develop the bending moment diagrams is a bit more complicated. So, for the shear force diagram, I just draw a line equal to the length of the beam. I say that this is point A, this is point B, and then this here is like the point where the point load is located. Now, what is the traditional way that we analyze internal forces? Think back to when we would look at axial loads. How would we analyze the internal forces, tension or compression? Well, I mean, it could be tension or compression, but like, I mean, how did we determine what the internal force was? What did we need to do? Look back at your notes if you can't remember, please.
Question again?
How did we analyze internal forces?
Internal equilibrium?
Yeah, but what do you have to do to the actual structure?
Cut sections?
Yeah, you have to cut sections, right? So what we could do is we could just cut a section here. And I'll just draw the force body diagram here. And what we'll have is just a line. We're going to have a vertical reaction force of 5 kips. And then lastly, for positive shear force, let me ask you guys this. What is the general tendency for the beam to go? Vertically upwards or vertically downwards under load? If you were to stand on a beam, which direction is it going? Down or up? Down. So because of that, the typical sign convention for what we call positive shear is down. So V is our internal shear force. And then usually wherever the cut is, we call this position X. All right? So you're considering the length of that beam X at the cut and everything to the left or to the right. So how do we determine V? What do you guys think the shear force is going to be?
Would it be the 5 kips over whatever X is?
Not quite. The reason being is because anything involving X would be a moment, right? Because then at that point, it's like, I'll show you guys how X kind of comes into play eventually, but right now with this load case, X has nothing to do with it, because if you were to just do some of the forces in the Y direction, you would just get the positive 5 kips minus V. And so you would find that the shear force is just 5 kips. So we're in positive shear, which means that the beam under loading is tending to slide downwards. Does that make sense? Now, let's cut a second section. All right? Where is this second section? I'll call this 1. The second section is going to be section 2. So we've got the force body diagram for section 1 and the force body diagram for section 2. What we have is a 5 kip force here, a 10 kip force here, and then cut section V. We know that this distance is 5 feet. And then we can say that this is our new distance, X. And we can label that X1 and X2. Just to be easier for the calculations. All right. Similarly, we just take forces in the Y direction is equal to 0. We have 5 kips minus 10 kips minus V. And we get that the shear force is negative 5 kips. Let me just change this over. And so our shear force is positive 5 and negative 5, depending on the location on the beam. Does that make sense to everyone? Now, we draw our shear force diagram. We know that this top part, left-hand side, is going to be positive 5 kips. And then this right-hand side, whoops, I'm lagging a bit. This right-hand side here is negative 5 kips. And that is the internal shear force diagram, Vx. Are there any questions about how we just got this diagram? No questions? All right. Now, there's a trick to doing these shear force diagrams. All right, this is something that makes the process a lot easier. because I'm sure a lot of you guys hate cutting sections and analyzing the internal forces, right? How many of you hate cutting the sections and having to do equilibrium each and every time? Raise your hand if that's the case. Great. I'm going to show you guys a really easy trick. Let's say that all of this just doesn't exist, all right? Let me just take this over here and just copy this. I'll slide this down a schmid. Whoops, come on. Come on. Just like that. And then I'll drag this over. All right. We determined that our forces were 5 kips and 5 kips, right? So now instead of having to cut sections, what we can do is follow the directions of the arrows by doing tip to tail. Have you guys heard of tip to tail? What this means is just follow the arrows, all right? We can see which direction is that 5 kip force moving, up or down. It's moving up. So you just draw a little arrow up. And this arrow is going to have a magnitude of 5 kips. Now, where is the next point load?
10 kips.
Yeah. Is there anything in between those 2 loads that's causing any change in the shear force? Such as, yeah, there's nothing. Nothing happening. So because of that, the shear force is going to remain constant until you reach the 10 kip force. From here, what you do is you drop 10 kips. So this entire height here is 10 kips. There's nothing across. And then lastly, you move the arrow up a magnitude of 5 kips. And so what you're left with is a positive shear force diagram and a negative shear force diagram. There are just some rules that you guys need to remember when you guys are doing this, which you guys will see as we do more and more problems. For example, with distributed loads, it is not just dragging the line straight across, all right? It's actually going to be sloped. And then depending on what type of distributed load it is, it could be quadratic, cubic. I'm not going to ask you guys those. The most I will ask you guys to do is linear slopes, okay? So that's how you draw the shear force diagrams using the tip to tail method. All right, let's do another example now. So now what I want is a beam. It has a pin and a roller. And it has a total length of, I don't know, 15 feet. All right? Now let's say that this is some really heavy W shape. Let's say that this here is, I don't know. You guys pick a W shape you want to use. Just come up with something. Preferably make it heavy. You guys want to use like a W12 by 100 or something like that? Yeah. Let's say it's like a W12 by 100. No idea if that shape even exists, but either way. What are the two important numbers in this?
100.
What does the 100 represent?
That's the weight, right?
Yeah. So when we take this 100 pounds per foot, what is that going to look like on the beam? Yeah.
1,500 pounds overall? Or are you saying like
Well,
roughly?
how would it look load-wise on the line?
A distributed.
It's a distributed load, all right? It's not a point load. The reason being is because if you consider it a point load, the shear force and moment diagrams will actually look different. And we're about to see why. So we've got a distributed load then here. And this distributed load is 100 pounds per foot. All right? Step 1 is determine the reaction forces. What are the reaction forces AY and BY? Can somebody tell me that? Yeah.
They both equal each other?
Yeah, but what's the magnitude of them?
Just half of the
Yeah.
load?
750 pounds. Everyone see how I get that?
Can you write it out?
What?
Can you write it out?
Yeah. So if your step 1 is static equilibrium, external. All right. Sum of the moments about A is equal to 0. And what the moment diagram and what your moment equation is going to look like is 100 pounds per foot times 15 feet. And this is just the force. Now, where is this force located? 15 feet divided by 2. From there, you add BY times 15 feet. Keep in mind the signs. The distributed load is going to be causing a positive or negative rotation about A. Use your right hand. It's a negative rotation. And BY is causing a positive rotation. So, from here, when you solve for BY, you should get 750 pounds. From here, do sum of the forces in Y equals 0. And you get AY minus 100 times 15 plus 750. And what you get is AY is equal to 750 pounds. And both of these are going upwards. From here, we move to our internal equilibrium now. All right, just to show you guys what's going on, I am just going to cut a section really quickly. Now, if this is a continuous load here, how many sections do we need to cut? Just one, because there's no discontinuity. So, if I were, my pen turned off, cutting a section here, we call this FBD1. What we are going to have is a beam, the distributed load, or the support reaction, its equivalent force, which was 750 pounds, and then the distributed load of 100 pounds per foot. And then make sure you draw your section. And shear is always positive, moving downwards. All right, I'm not even going to be testing you guys on using the opposite direction when you're drawing these shear force diagrams. Just always draw your shear force diagrams left to right, and it'll just follow all of these rules. If you change anything else, you will just start messing yourselves up because there are too many rules that I do not want to test you guys on. So just always draw your shear force diagrams left to right. And then the last thing we need is this distance x. Now, that distance x actually becomes important. Let's do sum of the forces in the y direction equals 0. And our force equilibrium is 750 pounds. And then what's the magnitude of the 100-pound force? It's dependent on the location of the cut. You guys see that? Because as you move further and further away from the support, you're adding more and more distributed load to counteract the reaction force, which means that as you move further away from the support, then less shear force is actually needed to balance out. Does that make sense? You look confused. All right. Let's think of it this way. Let's say that instead of x, we called this 3 feet. I'm going to leave x there, and then I'm just going to say, let's say it's 3 feet right now. All right? So what would our equation look like? It would be 750 pounds. And what else?
Minus 300.
Minus 300. And then what else?
Minus V.
Minus v. So what would v be in this case?
450.
450 pounds. Now, let's change 3 feet. And let's say that it's 5 feet now. What does it become? $750 minus what? Minus 500, and then again minus v. So what would v have to be now? 250 pounds. Is that higher or lower than what we had when x equaled 3 feet? It's lower. So less internal shear force is needed to balance out equilibrium. Does that make sense? We can generalize this by then, instead of specifying particular points, we could just write it in terms of x, which then would just give you 100x minus v, which means that the shear force is just equal to 750 pounds minus 100x. What does this look like? It's a linear equation, right? So it means that our shear force diagram has a slope. Sloped shear. So when we come over to here, we can follow tip to tail method again. All right? We're going to have a positive shear force of 750 pounds. But because of this distributed load, we know that it's sloped. How is it sloped? It linearly decreases just like this. I am just going to artsy this up a bit and just make it look nice. And the lines are not the same thickness, which aggravates me. So this becomes positive 750, and this becomes negative 750 pounds. Now we can check to see if this equation is correct. So let's say v when x equals, 15 feet. That's going to equal 750 minus 100 times 15. What do we get for the shear force at that point? Pull out your calculators. What do we get for the shear force on the right-hand side?
Negative 750.
Negative 750. Look familiar? It looks like this point here. And it also looks like our reaction force. So, this is an important note. Your shear force diagrams will always start at 0 and will always end at 0. If they don't close out, you did something wrong. Does that make sense? For example, if you computed the reaction and this was like 950 pounds and you got the diagram looking up here, does the diagram close out? No, it means you got to go back and check something. So, start at 0, end at 0. Now, what about x is equal to 7.5 feet? Well, what we would find is 750 minus 100 times 7.5, which is just going to be 0. So the shear force at mid-span is just 0. Now that's actually a really important point, which I will get to next class, because even though that's the point of minimum shear, it's actually the point of maximum bending. And you guys will see why next class, all right? But just keep that in mind. So it's usually good to note where the shear forces are 0. Are there any questions so far? Let's do yet another example now. This time, I'm going to have a pin here and a roller here. This is a 10-foot beam with a 5-foot cantilever. And there's a point load here of 10 kips, and then a distributed load on this side just going to shift this over slightly. Of, I don't know, I guess 0.5 kips per foot. And in this case, we're going to neglect the beam self-weight because, as you can see, the loads are going to be significantly larger. All right, so in a lot of cases when you're designing beams and then you apply a factor of safety, sometimes you can just ignore the self-weight because the loads that are imposed on it are usually much larger. But sometimes if you're like trying to really save money, you know, and trying to get as efficient of a design as possible and you're like at like 99% utilization, right? If you're failing to neglect for self-weight, it could actually cause your beam to fail. So just be mindful of that. That's why I do it. Just throw massive chunks of factor of safety and you can ignore self-weight. All right? So what I want you guys to do is just take a few minutes and tell me what the equilibrium is. All right? Tell me what AY and BY are. In the meantime, I'm You get it, Mike?
You're not gonna show me.
Alright. I think some of you might need help. That's okay. Alright. Now you guys know. You might need a little bit of practice with your statics. Alright. I'm gonna leave it here. If you need practice with statics, check out Engineer for free. .com. He goes over statics really well. Avoid the calculus topics, they are not needed, but he does a lot of like beam example problems just like this, and he does that really well. So, what we do, take moments about A. Set that equal to 0. And what we are going to have is negative 0.5 kips per foot times 10 feet times 10 feet divided by 2, because this whole thing here is the force. So it's a total force of around 500 pounds, right? 500 pounds per foot times 10 feet. No, is it? No, it's 5,000 pounds. So like 5 kips. My bad. Add by times 10 feet, and then the 10 kips with a total perpendicular distance of 10 plus 5, 15 feet. Negative, because it's rotating negative about A. All right. Do your quick math, so you can break down one thing at a time. Let's say, let me grab my calculator really quickly. Or not really quickly, because I don't know where it is. We could break it down one at a time, actually. So I'll help you guys out. So negative 0.5 times 10 times 5. This is going to be 0 is equal to negative 25 kip feet plus 10 by minus 50 kip feet. Carry the 25 and the 50, you get 75 kip feet is equal to 10 by. And reaction by is equal to 7.5 kips going up. From here, do sum of the forces in the y direction. And we have negative 0.5 kips per foot times 10 feet plus by, which we know is 7.5 kips, minus 10 kips. And then the last thing I forgot to add, which is the very first thing, slide this over a bit, is AY. And from here, you should get, let's see, $7.5 kips going up. Is that what everyone else gets? Double check my math. And I'm not just saying that as an excuse to get you guys to do it yourselves. Negative 0.5 times 10 plus 7.5 times minus 10. So then 7.5 minus. I feel like this is wrong. No, it is right. Okay. I was losing my mind for a second. I wonder what I did wrong in my calculator.
17.
What?
Because isn't 10 and 15?
Say that again?
In the sum of the moments of A, the 10 times 15 is supposed to be 150.
Yes. That's a good point. I'm rushing too fast. So this becomes negative 175, which means that's wrong, and that's wrong. First mistake of the semester. 17.5 kips. So negative 0.5 times 10 plus 17.5 minus 10. And you should get that AY is actually negative 2.5 kips, which means it's moving downwards. Now, for more complicated beams like this, I generally recommend just redraw your entire force body diagram. So, what we are going to have is a negative 2.5 kip force. What was the magnitude of the distributed load? 0.5 kips per foot. I'm actually going to remove this negative sign since the arrow is already doing the work. Change this color back to green. Well, not this. That should be black. Vertical reaction force was 17.5 kips. And then an applied load of 10 kips. Right? Did everyone get 17.5 and negative 2.5 for the reactions? Okay. So, now with our force body diagram redrawn, we just add the shear force diagram right below it. And follow tip to tail. Where does that 2.5 kip force go? Up or down? I'm asking you guys, up or down?
Down.
It goes down. So, it goes 2.5 kips down. Now, what do we do from here? We could cut a section and determine the forces, or better yet, just add the forces. Because what shear is, in simple terms, is the sum of forces. From left to right. So, we've got the 2.5 kips. What would that make the shear at this point? Was that somebody snoring or what was that? Oh, I was like, wow, am I that boring? Don't answer that. All right, so what we are going to have now is some shear force located roughly around here, right? Because the distributed load is going to reduce that value. It's going to continually add more shear force. What is the magnitude of this shear force? Well, we can call this V1, and we know that it's going to equal the negative 2.5 kips, and then we have to add the negative 5 kips per foot times 10 feet. What is this equal to? This gives us negative 7.5 kips. So that is the shear force there. Where do we go from here? Shear force 2. We take that negative 7.5 kips and we add the 17.5 kip force, right? Because that reaction force is going to push this way up. What is the magnitude of this force? 10 kips, and that's positive. I'm going to change this all to black, just to keep it neutral. Where do we go from here, guys? Is there any other load disrupting any of the flow of forces? No. So, what we do now is we just drag it straight across since there's no change in shear force. And then follow tip to tail down here. Clearly the shear force diagram is not drawn to scale, so I'm gonna fix that just really quickly, just because that bothers me. So it should look somewhat closer to this. And then the 10 kips would probably be larger, but whatever at this point. So let me ask you guys this. Let's say you were designing a beam. What would be the shear force you would use for design? Any takers? Yeah.
You would use the 10
10 kips.
Okay.
Yeah. Exactly. Pretty straightforward, right? Good. We'll work on a few more problems of these, but in the meantime, I'll give you guys a 10-minute break. Let's come back at like 7:15, all right? Cool. In the meantime, I do not have graded exams, but if you guys want to see what you guys got wrong, feel free to come up. Because I do have them all marked up. Except you.
I missed it. How is this the math?
Did PST plus PST plus 0.50676, even though you did all of this correct. It's PST 0.5076. You summed it wrong. I know that that sum is wrong because I have the solutions here.
I was worried these numbers were too much, so I'm happy I got it right.
Yeah, you got like 3.70246. The answer 0.507 plus 0.196 plus 1 is 1.7.
Oh, it's only
So you made a
supposed to be
math error
1?
somewhere. Yeah, so you
Okay.
added like 2 extra for some reason. It looks like you added this, and then just took the PST out and just said all of that is 1.
Oh.
So because of that, you added more forces than you needed to.
Okay.
It's a simple error. And that was really the only mistake, I think, for
In this
that
one.
problem. And I just pointed out that all the forces are greater than 400 kips. So that was your sign that it was wrong. But you'll only, I think, lose points for this. And then I noticed some students didn't find the stresses, but that's like a minor point. I'm looking more at your procedure.
Oh, good.
This one's the correct procedure. I think it
Forgot extra zeros.
extra zeros. Where is the 3 point? Oh yeah, 3.6. All right, but you just took the 3.6 directly from this packet here. I think you were rushing. Let's see. Wherever it is. You just took the 3.6. You failed to account for the 10 to the 6 or 10 to the 3. So that's another minor point, but correct procedure.
Okay. Oh yeah, this one. I knew this one was a problem.
That's a math error. Like, I mean,
Oh, that's all it was.
Yeah, like, I mean, that's entirely incorrect, you know?
I knew that.
Let me look at your flashcard. I just gotta see.
I wrote that one wrong. I remember.
No, I don't think you did. 'Cause I looked at it.
One of them is wrong.
No, because I remember I corrected it for
Yeah.
you. Yeah, it's just, you just didn't do the inverse of it. So that was incorrect. And then with this, again, forgetting to take times 10 to the 6, which is why this number is so massive.
I knew this number was too big, and I couldn't figure out why it was so big. Okay,
11.2 times 10 to the 6.
that makes more sense. I know, that was driving me crazy. That's what took me so long,
Mhm.
because I was like, no way it's this big.
And then
Right.
messed up the stress here. This is a calculator error. 90,000 divided by 3 is 30,000, not 3,000.
Okay.
So a lot of calculator errors, which
Yeah.
is, but I generally understand the procedure that you were doing, so that's why I'm saying you're probably gonna be somewhere in like the 80s or 90s.
Okay, that's good. I'll take that.
Yeah.
Thank you.
I'm just glad you recognized that that each material in a composite had a different force, because I had some students tell me that the forces were shared because of the true and false question. And that was their explanation. They were like, this is true because the true-false question I think is true. And I'm like, you can't just say you think it's true and make the problem true. Not how it works. Are there any questions about how to draw these shear force diagrams at this point in time? Or everyone's still understanding it quite well? All right. We'll just wait for Emily to come back. All right. Let's continue. All right. We have a cantilever beam now. And we want to figure out what the shear force diagram looks like for this. The beam is specified to be a W12 by 50. What I want you guys to do is draw the shear force diagram. So I'll give you guys actually a few minutes just to work on this. And I will walk around to help out as much as possible. I'm only looking after this stuff, whatever this class is. Yes. Nope. Remember, a cantilever beam is going to be entirely unsupported at the free end, which means that there are three internal forces or three reaction forces here. You guys don't remember? There are three types of supports that you can have. You can have the roller, which is equivalent to just a vertical reaction force here. You can have pin, which is equivalent to a horizontal and a vertical. And then you have the fixed. Let me just add lines here to represent the beam, which is equivalent to a vertical, horizontal, and a moment. So there is going to be an actual moment. All it means is it's just like, you know, it's not rotating at the free end. So it looks kind of like this. If you guys just get the reaction forces, I will be happy. Because then we can go to the internal forces. This is just more practice for you guys. We've got 500 pounds, 5 feet, but don't forget about the south weight because this is a relatively small load. So remember to account for how the distributed load would behave. So, what's your moment equation looking like? Well, take the moment about the reaction force. All right. That's one part. You write that. And then what's the other part? Not quite. There is no By. It's a cantilever. It's entirely unsupported. The other part is the self-weight. You notice how small the load is and the fact that I specified a beam? So if I ever specify a beam size, or if you guys are designing a beam, I will generally tell you guys ignore self-weight in the problem specifically. All right. Let me add that. It hurts. Who has did anyone have Professor Neiman for drafting with did she ever you know those architect scales? Did she ever show you guys the metal ones and be like, this is a lethal weapon? She's never said that to you guys? She said you can kill someone with this.
I have them, yeah, definitely.
She said you can't bring a knife to the campus or a gun, but you can bring this. And I was so worried. I was like, why would I need to bring a metal one? I love my metal one.
I'm a plastic one.
You have a plastic one?
Yeah.
No. After she told me that, I invested in the metal one.
Really?
Mm-hmm.
Who's your op, bro?
Who's my op?
Yeah. What beef do you have for people?
Dawson.
Yeah.
Metal one's too heavy for my back. My backpack already so heavy.
I just don't like the way it sounds, it like hurts me. Like walking around.
Just hearing that.
Just hearing the whole thing, yeah. I think that's why I prefer the plastic.
What's really annoying is the first one I got was in metric units, and she looked at me and she was like, you got an architect scale in metric units. What is wrong with you?
What would you buy?
It wasn't in metric units, but it was in like tenths of an inch instead of the typical 16ths. So she was aggravated. She was like, no. She was like, you're not in an engineering class. And I was like, I don't plan on being an engineer. So she was like, I was like, what's the difference? And she was like, this is an engineer scale. And I was like, 1 inch is 1 inch. Just like it is, but measure it to a 16th of an inch. I'm like, oh, boy. Did you guys figure it out? The reactions? Let's work on it together. All right. So this is a cantilever beam. As I wrote on the board, there is going to be 3 reaction forces. we are going to have a vertical force, AY. There can be a horizontal reaction force, AX. Whoops. But AX is 0 because there's no horizontal forces. And then we are going to have a moment MA. So, to determine AY, take sum of the forces equal to 0. And what we have is 500 pounds negative minus 50 pounds per foot of self-weight times 5 feet plus AY. And for AY, you will get 750 pounds moving upwards. To determine the reaction moment, you take moments about A equals 0, and that is going to equal negative 500 pounds times 5 feet plus negative 50 pounds per foot times 5 feet, and that's just the force, and then multiply it by 5 feet divided by 2, plus the reaction moment MA. And with this, you should get MA is equal to negative 500 times 5 minus 50 times 5 squared divided by 2, negative 3,125 pound-feet. Well, positive. Which would indicate positive rotation like that. Does that make sense to everyone? Great. So, now, just really quickly, I want to cut a section here because I want to show you guys something that's critical. If I were to cut a section just through here, and I drew all of the internal forces, so we're going to have the 750 pounds and then the moment of 3,125 pound-feet, and then a section cut here equal to V. What is the shear force V? Adding, of course, this, the distributed load. And then this is, of course, over some distance, x. Let's write our forces in the y equation. What is our sum of the forces in the y direction? Somebody just tell me what it is. Yeah.
750 minus 50x minus 8.
Exactly. What do you notice about the 3125? It's a moment.
Yeah,
It's not contributing to shear. So whenever you see moments, like point moments or whatever, although they may cause a vertical or horizontal reaction force in a particular member, the moment itself will never be included in the shear force calculations. So that 3,125, entirely useless for the calculation of V. So V is just equal to 750 minus 50x. So when we come over to our shear force diagram, we follow tip to tail, jumps up 750, and then because of that minus 50x, we know that it slopes down. Where to? We don't know what this magnitude is. But we can calculate what this point is, right? What is this point going to equal, guys? We'll call this V1. You guys tell me, what do you guys think that point is going to equal? Anyone? 500? How do you get that? Say that again?
I plugged 5 foot in for X.
Exactly. It's just going to be 750 pounds minus the 50 pounds per foot times the 5 feet. If you didn't have the shear force equation, you could still come up with that expression right there by just taking the full magnitude of the distributed load and just taking whatever your current shear force is and adding whatever the sum of that vertical distributed load is. So this gives us 500 pounds, which makes sense because then we have to add the 0.500 pound load, the point load of 500 pounds, which gives us a beam undergoing pure positive shear. What does that mean? It means that the entire tendency of the beam is sliding down with respect to a particular point. Make sense to everyone? Now, where does the moment eventually come into play? Comes into play next class, when you start developing the moment diagrams, because then it'll be a jump on the moment diagram because it's an immediate moment. But right now, I'm not asking you guys to worry about it. Let's do another example. Let's say now, I'm gonna actually give you guys something I've been dealing with at work lately, kinda. So, oh wow, I am drawing too many of these arrows. I want to move those over. Oops. And then move that over. All right. You have a fully distributed load. This distributed load is equal to, I don't even know what the self-weight of this segment would be. I want to say like 0.75 kips per foot. And then you have additional point loads here and here equal to five kips each. And the location of these are going to be given as shown. This is going to be 3 feet, 5 feet, and 3 feet. And then the location of these point loads in particular are 0.5 feet from the supports. And just to help you guys out a bit, I will calculate the reactions really quickly. Oops. The reactions are 9.125 kips and 9.125 kips. Yeah. What I want you guys to do is draw the shear force diagram for this beam. Those are the reactions in the green. Take a few minutes. Let me know what you guys get. Note I did step 1 already. External equilibrium is done. Sometimes I may do that if the problem is complicated. Looking good.
Here, if you like, because here there was a support here, which determines how far you would go for the shear force diagram, so here would just be.
Because there's no immediate arrow upwards, you need to slope it down. So that would be your start line.
Okay, so if there's nothing there, it's just a.
If there's no immediate arrow, so you can see all of these arrows are connected as a distributed load, which means it just slopes down from zero.
Okay. Okay, thank you.
Looking good.
So the V, just leave it like that. You can raise that solve that one.
Not quite, because that 0.5 is just a position. So it just means that the point loads are 6 inches away from the supports. But when you're drawing your shear force diagrams, what you need to do, well, you're forgetting the point loads, those have to be present here and there. And then you would just slope those down, starting from this point, because this distributed load, since there's no immediate force, there's no jump. So whenever you see the distributed load, it's just sloping. Well, you don't need to determine VFX every single time. No, you don't need the slope to do that. Like, here, if you wanted to determine how much it's going to slope down by, take the 0.75 tips per foot, multiply by 3 feet, and whatever that total value is the point that you drop down here. Then the reaction force, it jumps.
Oh, yeah, I was putting the distance between the actual units and then I was trying to do like that.
Yeah, you don't need to develop V of X every single time. You don't need the equations.
Okay.
No worries. If the equations help you visualize it, then
Yeah.
okay. But like, I mean, if you continually cut sections, it makes it a longer process. That's why it's usually better just to get comfortable with drawing these things. What do you got so far?
No, not fine, three.
Okay. Not quite. The reason being is because there's no immediate force located right here. So because of that, you can't have a jump. Instead, it's a distributed load, so it's just gonna decrease downwards, but from zero. So it's just. Exactly. You see that? So you shouldn't need to do all of this just because I already gave you the reaction forces. That's what the green is. Yeah. Let me clarify that. Looking good.
Cool question.
Yes.
Because I had to, this is the third time, after this,
There is a jump, but you notice how I specified that there's about 6 inches of spacing between the support and the point load. It means that it's gonna continue to slope downwards for about 6 inches.
right,
and you're
because
gonna-
of the distributed.
Yeah, from here to here. But then once you reach this point load, immediate drop.
Right.
And then just continue to distributed load, drop, distributed
Okay,
load.
that's, okay.
Does that make sense?
Yeah, that makes
Whenever
sense.
there's a distributed load, just slope it.
Okay, that's what I did before, but then I must have messed up, so I just erased it, but, okay, that makes sense.
All right.
That makes sense. But if you're gonna crack, so I see what you.
Yeah. And crack Bauer doesn't draw the shear force diagrams in the next 2 minutes. It's just fun to make the noise. Just here on the news, local Suffolk Community College teacher arrested for assault charges, accidental assault charges. Conspiracy theory, I actually broke Professor Dawson's ribs.
A pops fan showing up to work with a broken rib. But like, everybody was saying he was complaining about it. I don't get it, he was older, he was getting up there. I had this 70-year-old lady, like not 70, but she was like in her 60s. Her name was Ginger, and this is when I was gonna die. You know, she was a big drinker, and smoked like had a really raspy voice. She had like 2 broken ribs, and she was carrying trays full of food. I was just like, come on, like can't be that big. That's all. They can't be busy. Like, he fell off a ladder. This lady, I don't know, she like got into a car accident or something.
Oh.
But no, dude, she was like, you can't kill her. Like, she's gonna outlive me type thing. There's some note, like, this is what she used to do, bro. She used to take the fucking finger, used to say, like, you like the hand ginger, she did that, it was so gross. So, like, that,
Well, there's no immediate drop down, because you notice there's no plane loads.
yeah, I don't know, now it's lost, I'm confused myself.
All right.
I do understand, but I can visually understand why it goes down, or up.
You can see when it drops down and jumps up, but whenever you see basically a connected load that's distributed like this, it always slopes. It's not an immediate drop outward. All right.
Well, that's like,
Whenever you guys get it, or one of you gets it, then I'll go over it.
Christian.
Christian's got it? These are him or Edgar. Yeah, him and Edgar are gunning to it towards the end. Emily's not even close.
So you like this, right?
It's something like what?
You like this.
Yeah. Yeah, just draw out the general shape. So you've got that right, jumps up, slopes down. What do you mean? Yeah, but slope down still. No worries. We'll draw it out, but you've got the sloping right, all right, and then you've got the jump right. It's just determine the magnitudes and just keep adding the forces. So, for example, for this section here, you would just determine the total magnitude of force, and that's down here. Then you would add this, and that gives you whatever point that's going to be up here. Now, there's a distributed load between the reaction force and here, so you just add that.
What do that?
Let's see.
It's a crazy structure.
Exactly. Looks just like that.
Jesus.
Yours is a little bit not to scale, but like, I mean,
Yeah, no, that's good.
Yeah. All right, he's got it. I want to see if Edgar's got it. Oh, Edgar's close. That's actually what I have to do at work is for tunnel segments.
Yeah, how was that project?
Well, the main segmental lining design is entirely complicated, but just the stacking and handling part is what I was giving you guys. So you might have like a segment like this, right? It's supposed to be curved, but you'll have like forklifts here. And then you'll have like additional point loads from like load transfer here. And then additional segments up here. And so this would be like the forklift, and then these would be these segments stacked on top with some like wood block here as dunnage. And so that would be the shear force diagram for these segments.
How was the conversion though? Like,
What?
how was the conversion from like the Euro stuff to standard?
Oh, it's atrocious.
Yeah, but like, did you get there yet or no? Almost? Not even
Not even close.
So,
Yeah, we realized that we designed like 4 projects entirely incorrectly.
no, it's fine.
It's okay because fortunately we assumed conservative things, but we're like, yeah, moving forward, we gotta like fix this.
Pay attention.
Yeah. All right, let's go over it so I can give you guys your get out of jail. So, all right, first we want to calculate the shear force. All right, let's call it V1. What this point 1 is going to be is just that 0.75 kips per foot. It's negative since it's moving downwards, times 3 feet. The magnitude of our first point is going to be negative 2.25 kips. That's going to bring us roughly here. We can worry about the scaling later. V2 is just going to be that negative 2.25 kips plus our reaction force, which should give us 6.875 kips. Let me actually just make all of this black, by the way, just so that way I can keep it neutral. Come on, there we go. So, from here, we have to bring it up 6.875 or 9.125, and then that gives us a value of 6.875. So our second shear force point is here. This is 2.25. The red represents negative. Next, we can calculate a third shear force point. That is going to be for this little region over here between the support and the next point load. This is going to be 6.875 kips minus 0.75 kips per foot times 0.5 feet. Which is 6.5 kips. So it's a small decrease. That's 6.875. This is 6.5. From here, we're going to have V4, which is just going to be 6.5 minus 5, so 1.5 kips. So now we need to take our little arrow and drop it. V5 is going to be our existing 1.5 kips minus 0.75 kips per foot. And then you got to kind of figure out what this distance is, which that's just going to be 4 feet. 5 minus 1/2 a foot on either side. So that's 4 feet. Which this will give us negative 1.5 kips. So we just drag it across. Keep in mind, this diagram is not exactly to scale. That's going to be a 0 point, which it looks like it's going to be at midspan. For V6 now, we take that negative 1.5, and we also have to subtract that 5 kip point load. So we're looking at now the shear force at this location. So we take that and we drop it 5. Why am I adding K to everything? This gives us negative 6.5. We have V7 now. We take that negative 6.5, and we have to add the 0.75 times the 0.5 feet, which is going to give us negative 6.875. That is the distributed load that's spanning over here. And because it's only a distributed, it slopes just like this. We have to account for the reaction force now, which is going to be V8. So negative 6.875 plus 9.125. Gives us 2.25. So push it up. And then it's going to end up in the blue. So it's got to go up. 2.25. And then it should close out at 0 if you did it right. Because V9 is equal to 2.25 minus 0.75 times 3, which is 0. So we've got areas of positive shear, negative shear, just bouncing back and forth. Everybody see how the diagram was made? Are there any questions? No worries if there are. Is anyone confused by how I did this? Just gonna let it sink in for a minute. You just calculate each point and just keep adding more and more force as you go from left to right. Breaking up the beam basically into like 9 different sections, or however many sections it was. 1, 2, yeah, 9. Mm-hmm. Yeah. Any questions on this at all? No? All right. I'm going to give you guys one problem just to get out of here. Out of jail. call this 4 feet, 4 feet, and 4 feet. A, B, C. And yeah, that you're get out of jail. Once you do this correctly, you guys can leave. I already did it in my head. You guys like beams? No? Gets worse. Wait till next class. Remember that problem that I just gave you guys? Yeah. With the bending moment diagrams, you need to find the areas underneath the bid diagrams. By being good at geometry. Yeah. We will be doing a lot of these problems. And let me just stop recording.